In this assignment 8, we are having the polynomials as 1, 1 plus x, 1 plus x plus x square, 1 plus x square plus x cube, and then so on up to x to the power n, with the degree less than equal to n, forms the basis for v. This we need to prove. And in the previous assignment, we have already proved that 1 plus x, 1 plus x square forms the basis for v. But here the power is extending to n. So we are going to prove this result now. The example is, let V be the vector space of all real polynomials of degree less than equal to n, together with the zero polynomials over the field R, and prove that this complete set is a basis for V. So we have to start with the result that we already know that since none of these polynomials, the given polynomials, is a linear combinations of the preceding ones, which means these polynomials are already linearly independent. So it's clear from here that I'm writing the statement that since none of these polynomials or none of the polynomials 1, 1 plus x, 1 plus x square, up to so on, 1 plus x square plus x to the power n. So none of these polynomials is a linear combinations of the preceding polynomials. Fine. So from here we can say that the given polynomials are linearly independent. This is the result, right? So mark this as 1. One part is over. Then let's take one polynomial from V, right? And let me name that polynomial as f of x. I'm taking this polynomial as a0 plus a1x plus a2x square up to a(n)xn. Let this be a polynomial from V, and I will show that this polynomial is a linear combinations of the given polynomials, right? And it is also clear that fx is equal to, this time in the previous assignment I have taken the scalars to be alpha, beta, gamma because there are only 3 polynomials. So in this case I am taking the scalars to be alpha naught plus alpha 1, 1 plus x, here it is 1, then it is alpha 2 plus 1 plus x square, up to so on, and then alpha n 1 plus x square up to x to the power n, right? So this is equal to, if I add, so I will get alpha naught plus alpha 1 plus alpha 2 up to alpha n times 1, and then I'm having alpha 1 plus alpha 2 plus alpha 3 up to alpha n times x, then alpha naught, oh I'm sorry, this should start from alpha 2 I guess, alpha 2, yes, right, alpha 3 plus alpha 4 up to alpha n. So this is for x square up to so on. At the last I'm having only alpha n and x to the power n, right? Please note here this 1, x square up to xn, these are the standard bases for the vector space V, right? So these are already standard bases, right? And now I should write this alpha naught, alpha 1, alpha 2, alpha n in terms of a0, a1, a2, an, right? So for that I need to equate this 1 and 2, these two. From these two, if I equate, I will get Then because I need the values of alpha naught, alpha 1 in terms of a naught, a1, a2, then only I can say that fx is a linear combinations of the given polynomials. So let me equate this. So from here, if you look, the coefficient of 1, this is a naught, and here I'm having alpha naught plus alpha 1 plus alpha 2 up to alpha n. So I'm writing alpha naught plus alpha 1 plus alpha 2 up to alpha n. On comparing, this is equal to a naught. Then this alpha 1 plus alpha 2 up to alpha n, this is equal to a1, right? The coefficients of x. And then so on, alpha 2 up to alpha n, this is equal to a2. So on, if you go like this, you get alpha n to be equal to an, right? So this implies what is the value for a naught. So if you solve this, you get that a naught is equal to a naught minus a1. Sorry, this is alpha naught. Alpha naught is equal to a naught minus a1. See, this alpha naught is equal to a naught minus this complete sum from alpha 1 to alpha n, and that is nothing but a1. So I can write this as a naught minus a1. Similarly, alpha 1 is equal to, yes, this is a1 minus a2, very clear. Then similarly just go on and you get at the last alpha n is equal to an. Now I'm getting the values of alpha naught, alpha 1 up to alpha n in terms of a naught, a1, a2 up to an. Now I'm putting these values back in equation, this fx. Let me write this as star. I'm substituting these values in star. So I get alpha naught. Okay, already I have mentioned the values over here. So it is also written over here. Let me write that again. That alpha naught is a naught minus a1. Alpha 1 is a1 minus a2. Alpha 2 is a2 minus a1. Alpha n is an only. Now putting these values in the star, I get fx is equal to this, which means fx is now a linear combinations of the given polynomials, right? But fx was arbitrary, right? It is arbitrary, which means every element of v is a linear combinations of the given polynomials. Let me mark this as 2. So from 1 and 2, what is 1? That the given polynomials are linearly independent. And here I am saying that every element of v is a linear combinations of the given polynomials, which means the given polynomials are the generators of v. So from 1 and 2, I can say that these given polynomials forms the basis for v, right? Both the conditions are proved now. Thank you so much.